Australia, who will talk about structure-property relationships in molecular electronics. So when you're ready.
Yep. Okay. Hello, everyone. Thank you so much for introducing me with your nice word. I'm Masnun, one of the final year PhD student. I'm speaking from University of Western Australia. Last couple of years, I have been working on design and synthesis of different types of compounds to study the structure-property relationship in molecular electronics. Today, I will present a couple of my projects from my PhD work. First of all, we have been interested in controlling the flow of current through the material and understanding the science which leads to the technology. So here is the first solid-state transistor invented in 1947. And this is the transistor developed a couple of years earlier. Nanofabrication has allowed us to reduce the size of transistor from 10th of centimeter to the 10th of nanometer. As a result, you can see this transistor computer developed on that time. And now we are using current computer with reduced size and high functionalities. In the next step, molecular science is allowed us to put even one molecule between two electrodes, which can help us even get single nanometer size transistor, which gave rise to the field of molecular electronics. Molecular electronics is a field where molecule is used to control the passage of current between two electrodes. Now, when we put one molecule between two electrodes, it forms a junction. And in the next step, question arises, how can we measure the molecular conductance from a junction? One of the most widely used technique is scanning tunneling microscopic based break junction technique. Here is the STM instrument from our lab. If you amplify this region, you can see it consists of two electrodes. Top one is called tip, bottom one is called substrate. And during this measurement, we applied voltage and we measured the conductance versus displacement traces. First of all, in this technique, we put tip into the substrate layered with molecule. And in the next step, if we take out slowly tip from the substrate, at certain point, you can see one gold atom contact. At this point, if you go back to this plot, molecular conductance is really very high. Further pulling out, break the gold atom contact, and you can see from these traces again, there is a sharp decrease in molecular conductance. At this point, molecule can start to bind between two electrodes. And if molecule bind between two electrodes, there is a plateau like this appears in the traces. This is the molecular conductance of a specific compound. Further pulling out, break the junction, and you can see again from these traces, sharp decay of molecular conductance. So during this measurement, we collected thousands of different this type of traces. And if we compile them together, we get the histogram like this, where this peak is representing the molecular conductance for a specific compound, and this is the conductance for a gold atom contact. Now, we can model a junction using a rectangular tunnel barrier model, where when electron pass from one electrode to the other electrode, it needs to pass a certain barrier. And during this traveling, electron usually passes through a certain orbital from a molecule. Now, when electron is traveling, how do you know which orbital electron is traveling through? To understand this, we can calculate the Seebeck coefficient and we can measure it. So Seebeck coefficient is the current flow in response to the thermal gradient, which help to understand whether electron is flowing through the HOMO orbital or LOMO orbital. Here you can see from this picture, this is the hot electrode and this is the cold electrode. In case of hot electrode, Fermi function has get broadened. As a result, it has more electron upper than the Fermi level at higher energy. On the other hand, in case of cold electrode, Fermi function gets flattened. So it has more electron below the Fermi level. Now, in case of HOMO-mediated conductance, more electron from the cold electrode started to flow through the HOMO to the hot electrode, because this HOMO orbital is aligned with this electron, and which results in a positive Seebeck coefficient. On the other hand, in case of LOMO-mediated conductance, more electron from the hot electrode started to flow through the LOMO orbital to the cold electrode. Again, because these electrons are aligned with the LOMO orbital. And in that case, it gives negative Seebeck value. Now, from this experimental Seebeck coefficient value, whether Seebeck value is positive or negative, we can understand whether electron is flowing through the HOMO or flowing through the LOMO orbital. In our first project, we designed a series of two different series of compounds ranging from organic to organometallics. So first of all, we changes the molecular backbone. We used molecular diene, and then we insert one phenyl ring, and then we replace this phenyl ring with ruthenium, two different ruthenium fragments. And finally, we replace this phenyl ring again with platinum fragments. And on the in this series, we keep the molecular backbone same. We only change the anchor group to see the anchor group, electrode binding impact, how anchor actually bind with the electrode. Is there any difference to understand these things? This set of compounds are really good series of compounds because they have got very similar molecular length, and also they have very similar HOMO energy. So which can help us to understand the structure property relationship in a molecular junction. After designing these compounds, in the next step, we synthesized all of this compound by following some simple reaction procedure. The diene compounds are synthesized by simple oxidative homocoupling reaction. These oligo, arylene, ethylene types compounds are synthesized by Schroner-Garcia cross-coupling reaction. And finally, all these metal complexes are synthesized by simple complexation reaction. And here, these purple balls are representing two different anchor groups, thioether and cyclic thioether. After synthesizing all these compounds, in the next step, we measure the molecular conductance using scanning tunneling microscopic based Bragg junction technique. Here is the conductance histogram from this diene compound. So for the simplicity, I will explain only the cyclic thioether series compounds. Other series compounds also follow exactly the same trend in the experimental conductance value. So in this histogram, you can see x-axis is representing the molecular conductance. And this peak is the conductance for this compound, which is at -3.36. In the next step, we inserted one phenyl ring to these diene compounds, and you can see molecular conductance decreased to -3.66. This is because with increasing molecular length, molecular conductance decreased. After that, we replace this phenyl ring with platinum fragments. And you can see again molecular conductance decreased, although both of these compounds has very similar molecular length. Finally, we replace these platinum fragments with two different ruthenium fragments. And interestingly, you can see, although these two compounds has the very similar molecular length with other compounds, the molecular conductance increased a lot compared to platinum compounds. Is almost 1 order of magnitude higher, and is even higher than these diene compounds. You can see from these two compounds, we use two different ruthenium fragments, but they have very similar molecular conductance is same, which is telling us this ancillary ligands has very less impact on this conductance. Now, next question arises. Although this compound has very similar molecular length, but they have different range of conductance, experimental conductance value. So what is actually happening here? To understand this, in the next step, we studied some single parameter model. The first model was based on correlation of conductance with molecular length. which is telling molecular conductance will decrease exponentially with molecular length. So we plotted experimental conductance value against molecular length. Interestingly, you can see all the organic compounds are following this equation. That means molecular conductance decreasing with increasing length. But for the metal complexes, it's not following any trend. In the next step, we measure the Seebeck coefficient. And you can see the Seebeck coefficient value are small and positive, which is telling us all compounds are homomediated. So we studied another single parameter model, which is the correlation of conductance with tunnel barrier height. Although all these compounds from our designed series are homomediated, you can see from this conductance versus tunnel barrier height plot, both organic series and organometallic series are following completely different trend, but all of them are homomediated. So again, we can tell we can't explain this series of compounds by any single parameter model. Now, to understand and solve this problem, in the next step, we model all of this compound using Landauer-Batiker model. So Landauer-Batiker model is a DFT-based calculation which combine both molecular length and tunnel barrier height, and also all physical and chemical parameters inside the junction, and combine all these things together and give a complete idea about the junction. So we have modeled all of our synthesized compound using Landauer-Batiker model and calculated the molecular conductance. And after calculating this conductance, we plotted all theoretical results against experimental results. And from this plot, you can see experimental results are very good agreement with the theoretical results, which is telling us we can explain our synthesized and series of compounds only by Landauer-Batiker model. Now, Landauer-Batiker model based on DFT calculation is a bit complicated and time-consuming. Next question arises, can we make it simpler? To find out this answer, in the next project, we designed two different series of compounds. First series is the Tollens types compounds, where we maintain the same molecular length, but we varied the anchor group. And we synthesized both symmetric and asymmetric Tollens by following simple Shonogashira cross-coupling reactions. In the next series, which is oligoarylene ethylene based compounds, we designed and synthesized a series of compounds. We varied the central ring from thiophene to naphthalene to anthracene to understand the effect of aromaticity on molecular conductance. And in this series also, we varied different anchor group, and we synthesized this series of compounds by following the similar method. After synthesizing all of these compounds, we from the Tollens series, first of all, we calculated conductance value against the molecular length. And you can see from this plot, actually, again, molecular length is not following any trend with the conductance value. And in the next oligoarylene ethylene series, we plotted conductance value against the aromaticity of the central rings. And again, aromaticity also not following any trend with the conductance value. So which is telling us again, we can't explain these two series of compounds also by any single parameter model. To solve this problem in the next step, instead of using Landauer-Batiker model, we followed another rule, which is molecular circuit rule. This molecular circuit rule recently developed by one of our collaborators, Professor Colin Lambert from Lancaster University. According to this rule, we can divide a molecule into three independent scattering regions. One is the molecular backbone, other two is the anchor groups. So here is the list of molecular backbone and anchor group parameter. These are the calculated value. If we sum up these values using this equation, we can easily calculate the molecular conductance of a specific compound. After calculating the conductance of all these compounds using this equation, we plotted calculated conductance versus experimental conductance data. And interestingly, you can see experimental results is in good agreement with the theoretical results, which is telling us molecular circuit rule is a good, reliable technique which can compete with the Landau-Batiker model, and is definitely is much simpler and easier method, which can help us to predict the conductance of a design compound before synthesizing and measuring the conductance of the compounds. In the next step, so actually till now I explained the molecular conductance of a series of compounds where electron follow a single channel transmission in case of quantum tunneling, but electron can also follow more than one pathway. When electron follow more than one pathway is called multiple channel transmission, and which give rise to the quantum interference effect. As electron travel like a wave, during traveling from one electrode to the other electrode, if they follow the same pattern, at the end they can sum up, and which is called constructive quantum interference. During traveling, if they follow the different pattern, at the end they can subtract each other, which results in a destructive quantum interference effect. Now, constructive quantum interference effect has seen in a parasystem which give high molecular conductance, where here y-axis is representing the molecular conductance. On the other hand, destructive quantum interference has most dramatically seen in a metasystem, which give a very low molecular conductance with a sharp dQID. Molecule with dQID is very important to tune the molecular conductance near the Fermi level to get the device application. Next question arises, can we tune this molecular conductance, or can we tune this dQID? Yes, we can tune this dQID by changing the position of the substituent. If the substituent is at 4 position, this dip shifted to the right. If the substituent is at 2 position, this dip shifted to the left. And if substituent is at 5 position, dip remain at same position as the parent compound. This theory was proposed by Gamma Solomon. In our work, we proved the relationship experimentally. And we also found that conformation of this substituent also play an important role in molecular conductance. So in our project, we designed this parent system, and we chose O-methoxy as a substituent. When we put O-methoxy group at 4 position, you can see molecular conductance increased almost 1 order of magnitude compared to the parent compound. And here are the experimental conductance histogram. When we put it at 5 position, molecular conductance is same as parent compound as expected. Both of these are following the theory very nicely. But when we put the substituent at 2 position, you can see actually molecular conductance doesn't change a lot compared to the parent compound. So which is telling us actually in that case it's not following the theory. So what's going on here? To understand this, we move to the next step. And you can see here is the extracrystal structure for this compound, where O-methoxy group is sitting out of plane. So we modeled this compound and calculated the molecular conductance. We have found that when O-methoxy group is out of plane, lone pair of electron from oxygen can't communicate nicely throughout the molecule, which results in a sharp dQi dip with low molecular conductance like the parent compound. But if this O-methoxy group is in plane, which helped this lone pair of electron to move nicely throughout the molecule, and which increase the molecular conductance. And you can see from this graph, molecular conductance is really high. So this substituent can act as a molecular tap, where by changing the substituent conformation, we can tune the molecular conductance, where tap can be on and off by changing the position of the, conformation of the substituent. So which is really a great finding. So in the next step, now we are trying to design and put one sterically bulk substituent at this position, which can experimentally tune the molecular conductance by changing conformation. So in summary, in my work, we designed different series of organic and organometallic compounds by changing the molecular backbone and also the anchor group to study the structural property relationship in molecular junction and also to test different concepts of the theory. From the single channel transmission, we have found that molecular conductance for a specific compound can be explained by both Landau-Batical model and also molecular circuit rule. And in case of multiple channel transmission, quantum interference effect arises, which can be tuned by both position and conformation of the substituent. Finally, I'd like to thank my supervisor for his kind and generous support all the time and allowing me to do work in his lab. All my lab members for their generous support. CMCA for data analysis, collaborator for conductance measurement and theoretical calculation, and funding body Forest Research Foundation scholarship and Australian government scholarship for allowing me to do my research here in Australia. Thank you so much for your kind attention. Thanks a lot.
Thank you. Thank you, Masnun, for that presentation. So we can open up if there are questions from the audience. Please jump in and go ahead and ask.
Hi.
I'll ask a question. Thank you very much for your talk. You introduced various models. I can't remember the name. Lassiter was one, and there was another model in there. Presumably, in those models, they have a contribution for the molecular orbital distribution in your molecules. So the Landau, that's it. Not the Lassiter. Lassiter was fool's gold, I think, wasn't it? So in that model, presumably they have a contribution from the molecular orbital distribution. Have you ever actually calculated the molecular orbital distributions for your molecules and to see how that maps onto the conductance?
Oh, it's actually a nice question, but sorry, I'm a synthetic chemist. Actually, all these theory are run by our collaborator from Liverpool University and from Lancaster University. So actually, I never done these things.
No, that's okay. I was just curious whether people have, you know, sort of when you've read around the literature, whether people have looked at conductance with respect to the molecular orbital distribution, because you know, looking at some of the compounds that you've made, the organometallics would have a different molecular orbital distribution to the all organics, the anthracenes versus the naphthalenes and so on. And that may actually also be a sort of a feature that underlies the theory. But I was just curious whether you'd read around that.
Yep. Thank you.
Were there any other questions? I suppose just for my own curiosity, a little bit broader than your talk, but I guess these systems would be symmetric in the sense that you would change the polarity of the voltage and you would get basically the opposite current, right? There'd be no rectification happening. Would that be right?
Sorry, can you please repeat again?
That they conduct equally well in forward and reverse bias.
Yeah,
they would be symmetric.
Symmetric.
Yeah, I'm wondering, is it possible to introduce some asymmetry there and end up with a rectifying effect?
Yeah, definitely it's possible for not this series of compounds, but there are some research going on where people are getting rectification as an application from different series of compounds where we can actually get the different voltage. By applying forward and reverse things.
Would you need different metals in the tips or?
Yep. So we can use the same series of compounds, and we need different molecule to get this rectification.
Just different molecules. You still use 2 gold tips.
Yeah. We can use different molecules can use the rectification. I think.
Okay. All right. Were there any other questions? I suppose for either of our speakers. Rohan didn't have much time for questions at the end there. I kind of pushed him off. So if anyone has any other questions for either of our speakers, you can jump in. If not, then I think everyone please join me in thanking Masnun and Rohan for their talks today. So we will be back with another seminar next month. So we're doing this monthly. If you are interested in speaking, then feel free to send an abstract through. So my email address will be at the bottom of the invitation that you would have received. So thanks everyone, and we'll see you next month.
Yeah, bye.
Bye-bye.
Thank you for the opportunity. It was really nice. Bye-bye.
Of course, you're most welcome. Bye-bye.
Yeah, thank you for organizing these, Bronson. Really much appreciated.
Yeah.
Of course.